we said that x uppercase omega, that's Fourier transform of x of t, time domain signal. How you find it? Using integration formula, make integration from negative infinity to infinity. After multiplying this function by e to the power of minus j omega t dt. And omega is continuous from negative infinity to positive infinity. And we mentioned the even function, the odd function, how we express this integration in rectangular form, polar form. And you got to keep up with this course, because every week you will have many topics. And if you don't follow up and then you want to get it after 1 week or 2 weeks, you'll find it very hard. You'll forget it because you have another topic coming. So my advice to you, keep up with this course, because every time you have a new formula, then you will be messed up. You know, if you say, okay, I'm going to collect in 2 weeks before the exam, for the quiz, it will not work. Especially that we have different topics, like what we did for your series. We make Fourier transform for continuous time, and then after we finish this, we are going to start discrete time Fourier transform. It's different form, so it's just you have to keep up. It's not difficult, but you have different formula, and if you practice, it'll be very easy, direct application. So the last example that we did, the rectangular pulse, and this rectangular pulse, it was like that in general. And it's from minus tau over 2 to plus tau over 2 on time domain. That's x of t, and the height is equal 1. How you write this one? We use this notation. We see p tau of t. What does it mean? A rectangular pulse of width tau, and that's the width from the negative to positive. If you add them, you got tau. That's the width. Some textbook, many also, they can use this one. Say rect, mean rectangular pulse, and t over tau in time domain, and then you make it tau. This is the width, the center. So if you see this notation or this notation between that. Anyway, we found Fourier transform of this signal, and it was found to be equal to, of course, we use numerical value, but I'm making now in general for x of omega. It was equal to tau sinc tau omega over 2 pi. And we said that's the first time you are introduced to the function sinc. And it was toward the end of the lecture when I explained what does it mean sinc function. So let's just a little bit make it general. What is sinc function? Sinc function, what's written like that, sinc, let's say of z, general. That will be equal to sine pi z divided by pi z. It's like normalized sinusoidal way. So that's the definition of sinc. We can sketch it. To sketch this function, we'll have x-axis that will be according with z, and the same. If you substitute by z equals 0, the first thing, what you'll get when z equals 0? It'd be sine 0 over 0, right? What is the value of sine 0 over 0? Huh? Oh, I couldn't. No. No. You had it in, okay, let me remind you in math. What is limit? Sine x over x when x tends to 0. It's equal to 1. Why? Because if you go for the unit circle, that's math. I should explain, but just I try to make it look familiar to you. If you take a small angle delta, what is the sign? And let's say that this is unit circle, means the radius is equal 1. So what is the sign? Sign is the opposite, right, over the hypotenuse, which is 1. So this length, the perpendicular, you can see that it's almost equal to the arc length, right? Let me make it bigger. This is the arc. That's the radius 1. That's the angle, and that's the perpendicular line. I make it far a little bit from the edge. Should be here. So if you call this y, so y over 1 is equal sine. But y, when you make it very small, you'll find the length of this one is almost equal to this one. The arc length is equal to the perpendicular line y. What is the arc length? You got in math, arc length r theta. The length of the arc is equal r theta. If this is r and this is theta, so the length is equal r theta in radian. That's the length. So both are the same, right? So when you say that y is equal r theta, so now the sign, instead of writing y over 1, I remember our r is equal to 1, or even if you take it any value, the value of y over r, that's the sign, theta. However, y is equal r theta when it's very small, getting close to 0. So I carried this y by r theta. So r theta divided by r, that's the sine theta. Okay, so that will cancel. So sine theta is equal theta itself, right, in radian. So it's equal theta. Great. I want to find limit sine theta by theta when theta approaches 0. Well, sine theta now we say that's equal to theta almost when it's 0. So what is over theta? 1. So that's why even you do it in the calculator, don't make sine 0. Make sine 0.001. Sine 0.01. 1 over 100 over 0.01. You do it in the calculator, find is equal 1. So every time the angle is getting smaller, so that's why the value of the sinc function, it will be equal 1 at 0. And every time you are increasing the angle, the sine is divided by, and also increasing here on the bottom, so you'll find it takes the shape of the sine like that. But because I divided by pi z, I find sine by z and divide, so the amplitude will not be the same when you go to negative. It would be like shorter, and then it will flip it, go again, be shorter. So every time you are increasing theta, you are increasing theta in the bottom of this fraction. So the amplitude is decreasing. So it's like sine, but, and of course on the negative side will be symmetric. That's the sinc function. That's the sinc function z. So let's just remind you what is happening. That is the Fourier transform of a square wave rectangular pulse, limited interval. So that will be, if we sketch it, that will be the frequency response. What do you observe? You observe that the amplitude of the frequency spectrum, it's the highest value when the frequency is equal to 0. And every time you are increasing the frequency, because the frequency in this case, why I'm saying the frequency, because that's x of omega, and omega is the frequency. I just was showing the z in general, so you can deal with it. But that's what you got, tau, zinc, tau, omega over 2 pi. So that's sinc function of omega. So if I'm sketching now the same thing, just I change it to omega, I still have the same thing. So that's x of omega now. The only thing I have here tau, so just I'll make the tau the amplitude. Right. So what's happening now? At low frequency, the component inside the square wave, it's high. And every time the frequency is increasing, the amplitude is decreasing. So at high frequency, it will vanish. So it's like focused. It's focused the all frequency in the middle, around the zero or around the low frequency component. It has low frequency component more than high frequency component if we have a square wave. Yes, you can do the amplitude. This is only x of omega. That's strange. That's the first time we sketch the frequency response on one graph. Why? Because a special case, x of omega is a real value. If it was a complex value, when we did the exponential, if you remember the example, we did exponential, the first one. We got like 5 over 5 plus j omega. That was x omega. That was the frequency the frequency component, or the Fourier transform. It's complex. You cannot sketch it. So in general, you cannot sketch x of omega against omega. It just happened in this case because x of omega was real. That's why. But in any case, you are required to sketch the amplitude of the frequency component and the phase difference. Well, let's do that. I will sketch it on the same graph. If you wanna sketch the magnitude, we call it A, right? The amplitude of the Fourier transform x omega. How will do it? You will say A is equal the value of x of omega. What's different between the amplitude and this graph that we have?
We have negative value.
Exactly. We have negative value and always amplitude, positive value. So what you'll do, the all negative value will be reflected here. And you will just erase this. So everything will be a positive value. That will be the amplitude. And of course, observe the difference is obvious between Fourier transform and Fourier series. Fourier transform, you just were in the lab like 1 day ago, it just sticks a discrete value. Find the amplitude at omega naught, 2 omega naught, 3 omega naught, and even you use stem to plot it. But this one you use plot because you can find the frequency at any real time, at any real value of omega. So that's the amplitude. Well, what about the phase difference? How you do the phase? Let me go back to the original. Let me do the first, the positive, and I'll make it bigger a little bit. So, well, that's the right hand, and I'll make the phase. Phase means the angle, all right? So I will do it. Up to this point, what is the angle? Up to this point, from 0 up to this point. Yeah, 0. Why? Positive value. What do we agree about? Positive value, it's 0. The angle is 0. Negative value, 180 or minus 180. Both are the same, right? If you go there, there. All right. So up to this point, it's 0. That's right. From this point to this point, pi, right? 180. So you would say the angle is pi. And again, that will be 0, and that will be pi. So, and you continue like that. Let's go to the left-hand side. It's symmetric. I mean, that equidistant, the same amplitude, the same intervals. It's symmetric because we said that's symmetric about y-axis. All right. How you do the same thing? It's positive will be 0. What about from this point to this point? What is the angle? Negative. Why we make it negative? You can make it positive. Positive 180 and negative 180 are the same. But why here we mean negative? Because we said that the phase spectrum is odd function. If you make it the same pi, it will be even function. No, even function only for the amplitude, the one we did in the top. So you make just negative pi, 0, negative pi, so on. So that will be the phase of the frequency spectrum of the square wave. So that's the frequency transform of the square wave or square pulse. And as you said, that you see the amplitude of the spectrum is decreasing with frequency. So it has more low frequency components than high frequency components. Okay. There was an example that we did before, and you should try it also. How can you find the continuous time Fourier transform of a rectangular pulse? What's a rectangular pulse? Rectangular pulse like that. And I put it in the practice. That's x of t. And let's define it like that. Tau over 2. I'll just make it similar to the rectangular pulse. This is that's triangular pulse. Negative tau over 2, and amplitude is 1. How we'll write it? We'll agree about the way we say this is triangle pulse, tau of t. But you got to know how you describe this signal in time domain. How you write it? You can say it like that: x of t equal to. You can divide it into 1, 2, 3, 4, 3 regions. Something outside this region that will be 0. Let's focus now between negative tau over 2 and positive tau over 2. You can say that the time when greater than negative tau over 2, less than 0. Then you try to find the equation of this straight line. Okay, the slope is equal to what? Positive slope, right? The slope is equal 1 over tau over 2. It means 2 over tau time. And what's the intercept at 1? So we can write equal. Let me make bigger space here. So you can write x of t equal to 2 over tau t plus 1 for this region. Let's check if this is the right equation or not. If you put t equals 0, it will be 1. That's right. If you put t equal negative tau over 2, negative tau will cancel tau, 2 is cancelled, negative 1 and 1, 0. That's right. So that's that work in the interval negative tau over 2 t less than 0. And for the second region here, where t from 0 up to tau over 2, it will be the opposite. It's y-intercept the same 1, but the slope will be negative, so be negative 2 over tau t. Let's check. If you put t equals 0, it's 1. Or if you put t equal tau over 2, that's right, 0. That's right. And 0 elsewhere. So that's another way to represent the triangular pulse. Obviously, you can reduce it because this region and this region, they are the same. So I feel that you can use like modulus or absolute value for it because this is exactly the same, just you are using modulus. So what about if you write it like that? If you look for the table, I just give it to you. because I need to fix something here. You'll find this paper has two. One is properties. No, just look for the first one. Common time, a continuous time Fourier transform, common Fourier transform pairs, and you go for which line? There is a one that has like let me count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10. The 10th line. You'll find written like that: 1 minus 2 t over tau p tau t. You can write in the front here, that's the rectangular pulse. That's how you express it. Let me explain to you why it's written like that. I did for you the easy way. It's 2 over tau t plus 1. All right. If you get the equation, you have 1 minus 2 tau t. If you put the modulus here, that will work for both. But there is no interval here. This equation, if you write this equation, let me write now. If you want to sketch 1 minus 2 over tau t, it will be straight line. Like what? Like that. Because you don't define the interval. If you just write like that, 1 minus t over tau over t. And that would be negative tau over 2, positive tau over 2, and that's 1. And you can check. Check. Put t equal to negative tau over 2. It will cancel the negative, and then will be 0. That's right. And it can work everywhere. But the definition only from negative tau over 2 to positive tau 2 and 0 with the rest. What you'll do, said, okay, if you multiply that by a pulse, unit pulse, like that, equal 1. When you multiply 0 by this will be gone. And this will be gone. And this 1 by this, that will be left. So that's how they write in the table. I want you to understand. I can tell you that the triangular pulse, and it works, and they will do fine. But I want you to understand why they are doing this. If you remember, always we use multiplied by u of t, u t minus 1, just if you want to express any signal in limited interval. So this is the way. That's why when you look at the table that you have, that this pulse is equal 1 minus 2 tau, absolute tau over tau, t over tau, and then the rectangular pulse, this one, this is the one, just to define the interval. So you don't have to write the whole thing here. Continue on the same line. You'll find arrow with 2 sides. What does it mean? It means in this table, if the signal in you that you have it, you want to find its continuous time Fourier transform without doing integration. If you're unlucky, you can get it and put the result directly from this table. Well, we want to prove that. We did the pulse, right? We did the pulse, the rectangular pulse. But let's just work on this one because I want to do correction in this one. You go to continue on that in the line 10, tau over 2. It's written tau over 2 sinc square tau omega over 4 pi. Please delete pi. Mark it out. That's not right. Xbox made a mistake in this one. Just remove pi. So what is that? That's x omega. That's the continuous Fourier transform for triangular pulse. So what does it mean? It means now, without integration, you can do this table. All right? So we'll fix this one. Let me give you one problem to solve it in a minute. What about if I ask you, find Fourier transform, and I don't give the equation, just I give you something like that. Equal to minus, plus 1.5 minus 1.5, 2. That's x of t. And that's t. Find x of omega. If you do integration, you will spend half the class time to do it. Because you will integrate, you will have t, right? t times e power minus u, then you start integration by parts and all the thing. No, I want you to use the table that you have to find Fourier transform for this function. Go ahead. Using the table. Yes. You didn't have this? For me? Yeah, there's the error in the 10th line. Let me write the 10th line here. That's yes, 1. That's number 10, line number 10. 1 minus 2 others t over tau, pulse tau, and then it's given tau over 2 sinc square tau omega over 4 only, not over 4 pi. Yeah, so cancel pi. We're going to use this solving many problems. So anybody solved the question? Yes, you did?
3 over 2 sinc squared.
Let me just write your answer, okay? 3 over 2 sinc square, yes?
3 omega.
All right, let's check the answer. So what you'll do, you look for the diagram and try to find tau. So what is the tau? That's tau over 2, right? Make sure that this is the same. So you will say tau over 2 is equal to 1.5. So tau is equal 3. So that's the first thing we got. So remember, triangular pulse, its amplitude is equal 1. The amplitude is equal 2. So what you do, I'm going to, if you multiply 2 here, you multiply 2 here, right? Because you have amplitude equal 2. So x of omega will be equal to times tau over 2. I replace tau by 3. Sinc square tau is equal to 3 omega over 4. Cancel. So the answer is equal to 3 sinc square 3 omega 4. It didn't take more than half minute. If you do to the integration, that will take a long time. They call this Fourier pairs. Fourier pairs. All right. Even you can get the rectangular pulse that you did before, you can check it with the same table. And you, yes.
So at the beginning, it's supposed to be tau over 2, right? And tau is 3.
Tau over 2, yes, because this formula based on that, on this tau over 2, negative tau over 2.
Right.
So then you figure out what the value of tau and you replace it, yes.
So wouldn't that be 3 halves?
Tau over 2, but tau is equal 3. So I have tau is equal 3 over 2. That's right. 3 over 2, yeah. And that's, I have 3 in the top. Tau 3 over, yeah. What's the problem?
Well, I'm confused by the same part. Why was it multiplied by 2?
Because the amplitude is 2, not 1.
Oh.
And you see what I did, the two in blue here, and I multiplied by 2 because the amplitude is 2.
I see.
If it's a normal triangular pulse, will be 1. Let me show you that. That's what we did. That's 1. Even the rectangular pulse amplitude is 1. Standard pulse. Yes. Any more questions? That's good. That's good. Yeah. Actually, what you did in many quizzes, many students they missed it, but they just would forget the 2. Yeah. So you got to adapt. All right. And you can check even the example we did before. You'll find exponential with it. Just you can review when you review lecture. Check. But now let's do something important. Since we have the table, so we can find everything easy. Of course, if I have the table, why I'm going to integrate? But why I taught you integration? Because in some function, if you don't have it, you will do it, and you know where it comes from. But after that, use the table intensively as much as you can, if you can. And I'm going now to teach you some properties of continuous time Fourier transform in a way that it can increase your usage of this table, if you know the properties. And they are so important. You will use, even you are going to apply to whatever you're going to study, communication or power, whatever, you're going to use the properties of Fourier transform. Let's start with the first property. Yes, the first property called linearity. So we are going to do now properties of continuous time Fourier transform. The property number one, linearity. What does it mean? If you have two signals, x1 and x2, and you multiply this by constant A, you multiply this by constant B, and you add them, you still can find Fourier transform. Simply find the Fourier transform of x1, that will be x1 of omega. Find Fourier transform of x2, that will be x2 omega. Multiply the first by A, the second by B, and add them. It works. All right. Let me give you a problem. I'm not going to explain every single problem. I'm going to give you a chance to solve, and then I will correct. That's the best way to learn. So the first example that I'll give it to you, and try to apply the linearity. Something like that. That's 2, 1, 2, and you got 1, 2, -1, -2. That's x of t. And the question is, fine, Fourier transform this one. I'll give you 2 minutes. What you're going to use? The table. And I'll make it simple. What do you need from the table? The pulse. Rectangular pulse. What's a rectangular pulse? Let me write for you. Rectangular pulse. I'll make it simple and fast. It's P tau, and written like that. That's time domain. Tau sync tau omega over 2 pi. That's number one. And using the linearity. So you have the old formula that you need. You have the property, you have the property, and you have also the pair. Go ahead. I'll give you 2 minutes. Can you divide this signal into 2 signals and you add them together, you get x of t? Yes. You can add 2 rectangular pulse. Think about the duration of each one, and I made now very simple. 2 rectangular pulse. If you add them, you get this one. So just find the duration of each and the amplitude. That's all. Yeah. It's better just to sketch it here, 2 separate graphs, and check it in your head. Because there is some connection. Something, if you pay attention, you can get it.